Okay, so in the last class we had been playing around a bit with checking phone numbers to see if they looked right. And that's one of the main jobs of JavaScript, is checking user input to make sure that it looks like it's supposed to look. And as we're going to see later, possibly in this class and in other classes, over the years people have developed lots of different techniques and stuff to help catch mistakes and catch errors. So that's one of the most useful things that JavaScript does. It's very handy because, you know, let's say you're entering a credit card number. That's a classic example, okay? And you make a mistake. Well, then the web server, that goes back to the web server. Then it connects up to the bank. And then the bank goes, no, that's a make-up number, that's no good. And then it comes back, and then it comes back. Wouldn't it be great if you could actually, I mean, if you say your credit card number is, 88401. Do you know? Like, the web page is able to say, well, come here now, like, where's the rest of it? Do you know what I mean? I'm not sending that off. I know that's no good. Don't be codding me. So there's no point in the web page sending that to the web server, to the e-commerce engine, which is going to send it to the bank, which is going to say, well, actually 884015 isn't a valid credit card number. You're like, duh, I know that already. So that's one of the jobs that JavaScript can do, is check things for how they look. So what can happen is, this diagram didn't turn out quite the way I was expecting. There used to be an arrow here, but so if it's not okay, it basically just goes back and asks the user to enter again. So if you enter 884001 as a credit card number, the JavaScript will look at that and say, it doesn't look like a credit card number to me. Maybe you should put that back in. So you see that a lot on websites where they ask you for an email address, or where they ask you for credit card number, for a date of birth, things like that. If you put it in, if it doesn't look right, it'll come back at you. One thing that annoys me is it looks for postcode, and there are just so many people in the world cannot fathom how a society could function without postcodes. But it's not chaos. So if you buy things online, very often in Ireland you're used to just making up postcodes. No. So as we saw, Irish mobile phone numbers begin with a 0 and 8, and then you can have a 3, a 5, a 6, or a 7, or a 9. You don't have 8 because that was analog, and then 7 digits after that. Okay? And we saw this code already. That's the same code we saw before. Now, imagine, right, okay, you go to a bar that has like the beautiful people in it, okay, and one of the beautiful people seems interested in you, and you wake up the next morning and you find in your pocket call me and a number. No, yeah, if the number is like 087 5512, well, you're not going to rush out and book the most expensive restaurant in town. That's one of the beautiful people toying with you. Okay? Now, imagine, for years the beautiful people were toying with you, and then, as you know, success is the best revenge, and you got a great job and you became, say, the telecoms regulator of Ireland. Suppose you were going to make it your mission to make it hard for the beautiful people to toy with us mere mortals, right? And you're going to say, well, from now on, right, we're going to have some rules about phone numbers. So let's say, from now on, right, the last digit of every phone number has to be equal to the number of even digits in the start of the number. And see, the beautiful people often aren't that bright. So this might be too complicated for them. So it'll make it harder for beautiful people to make up their phone numbers. Okay? Because they would have to follow these rules. So any randomly generated phone number would only have a 1 in 10 chance. Well, actually, no, it's not 1 in 10. It's different, but It's smaller than 1, it's better than 1 in 10 actually, but any randomly generated phone number, you know, might not actually pass this test. So when you wake up the next morning with the call me, would love to meet you again, and you see the phone number, you could apply this test to it. And then if it passed the test, you could rush out and book the most expensive restaurant in town. Okay? So this kind of thing is called a checksum, or a check digit, or a check letter, depending on the situation. And typically, it's some mathematical jiggery-pokery where you put this extra piece of information in and it has to match up with the rest of the information, and if there is a mismatch, then something's wrong. Okay? So, these are all over the shop, and we look at some of them. And they're great. Programming lecturers love them, do you know? Because you have to do loops and all sorts of things to work them all out. So programming lecturers love them. It's mostly what JavaScript does all day, is check user input. So you can imagine a class in programming in JavaScript, sure. It's just what we want. No. So we get what I'm talking about. So if someone says their number is 087-999-6664, that's wrong because it should be 1, 2, 3, 4, 5. There are 5 even digits in that number. So that should be 5. So that's just one of the beautiful people toying with you. But fear not, you shall have your revenge. Now, to be honest, they're usually much more complicated than this. Okay, this isn't a very good one. This is just an example I made up to give you the idea. Okay, they're also a bit inefficient because if you were to implement this scheme when you become the telecoms regulator, like the phone companies would be very pissed off with you because you would be down. You'd reduce the number of possible phone numbers to 10% of what they are now. You're missing a whole digit. So probably what you'd have to do is you'd actually, if you were going to do this for real, is extend the phone numbers so that there was 8 digits and the last digit was a check digit. It would also be great as well for wrong numbers, do you know what I mean? Someone puts in a wrong number. Now, to be honest, people don't get wrong numbers that much anymore. It's not a big problem that society needs to solve. But you could see how if you had a scheme like this, you know, the phone company could check before it rings. Well, that actually number, no, that doesn't make sense. You must have a mistake there. Do you know? No. So credit card numbers do this, right? The last digit of a 16-digit credit card number is the check digit. Now, if a number looks okay, I mean, the person could still be broke. Like, the card could still be stolen. I mean, but it makes it harder to just come up with a totally make-uppy number. Now, of course, if you know this and you're in the business of making up credit card numbers, then it's very easy. I'm saying it makes it harder for someone to make a mistake. So if you type in the number wrong, it'll probably catch it. There's a good chance of it being caught. It doesn't really prevent fraud. Okay? But it just means if you make a mistake when you're typing in your number, the web page will catch it and say, oops, I think there's something wrong there. Check that again before it sends it off. So, this is where you all whip out your credit cards if you have them. No. So, I guess the guy who devised this was Loon, or I'm not sure. We'd have to look up where he's from and then we could figure out how to pronounce his name. We'll just call it Loon anyway. So the Loon Formula for credit cards. And it's an algorithm that you use. So, starting with the second last digit of the number. Now the reason you do that, by the way, is if the last digit is the check digit, typically you don't fiddle with that. So if ever you're trying to remember what the algorithm was, well, you don't really multiply or do anything to the last digit. You leave that alone. So starting with the second last digit, you go every second digit, okay, you multiply it by 2. So every second one gets multiplied by 2. Then you add those digits together, We'll see that in a second. So if you get like, if the number is 9 and you get 9 plus 9 is 18, well then you do 18 is 1 plus 8, gives you 9. Right, so it's easier to see than it is to explain in words, really. And then you add up all those numbers together, all of them, the ones that were modified and the ones that weren't, and then the result should be evenly divisible by 10. So it's easier to look at the maths than it is to actually do it. So every second digit gets multiplied by 2. Okay? So 2 times 2 is 4 here, 7 times 2 is 14, 0 times 2 is 0, 0 times 2 is 0, 8 times 2 is 16, and so on. Now, you add the digits together then, so 1 and 4 becomes 1 plus 4 to give you 5. And 16 becomes 1 plus 6 to give you 7. Now, in terms of programming, actually, that's a right wild pain in the arse. But it does turn out, and you could find a maths person who could prove it to you, that if the number is greater than 10, I think, I'll probably get this wrong now, but generally what you can do here is, like for the 14, if you do mod 9, you will get 5. 16 mod 9 is 7. I'm just thinking though, the example I plucked out of the top of my head there, which is 9 plus 9 is 18, and 18 is like 1 plus 8 to give you 9, but that's 9, not 0. Because 9 mod 9 would give you 0, wouldn't it?
Yeah.
So,
Well, it was 9 plus 9, I mean.
of course 9 isn't over, no, well of course 9 isn't greater than, well no, hang on no. Yeah, 18 mod 9, oh no, 18 mod is 0, yeah, so that's,
0,
so it doesn't work there. So you might have to put in some exception for 9, okay?
18.
There is a way to do it in general, though. If you use integer division by 10, and then you use modulo by 10, it'll give you that 1 on the left and 4 on the right for any digit that's 0 and 99.
I totally believe you, because you said that with such conviction. But say it again. Say it again.
If you do integer division
Integer division by 10.
if you divide 9 by 10 integer division, you get 0. But
Right.
the modulo by 10 then will give you 9, so that's 0 and 9. But for 14, you would get the integer divide will give you 1, and the modulo will give you 4. So you get 1 plus 4 times.
Yes, that's the mathematical equivalent of taking the first digit
Yeah.
and taking the second digit and sticking them together.
Oh, alright.
Yeah.
You gotta think first, second.
Yeah.
stick it
So,
there.
I mean, that's what you'd be doing if you were doing this, because you don't want to be screwing around with strings, actually. Anyway, let's not get to it. So this is the algorithm, okay? We'll look at the algorithm and we'll worry about the implementation a bit later, okay? But what you're talking about was the long way, and I'm trying to find the short way. But I'm not sure it works for me. Anyway, so you get your numbers and you add them all up, okay? And you get a number. And if that number is evenly divisible by 10, so if that number mod 10 is 0, then yip-de-doo, the number looks legitimate. And the last digit is a check digit. So actually, sometimes if you get, let's say there's a couple of people in the house and we're all getting new credit cards. You might find that the first person gets 742, and the next person gets 743, and the next person gets 745. Because that's the sequence, and the check digit then is chosen to make things match up. Similarly, if you go to the bank and you get lovely smell of new money, if you look at the serial numbers and you think these should all be in sequence because they're all one after the other, they'll appear not to be in sequence, but if you ignore the last digit, they will be in sequence because they are in sequence. Just the last digit is the check digit. So you get the idea there?
Yeah.
So that's the algorithm, and no. And you can also check sort of just the look and feel of the number. So Visa card numbers can be 13 or 16 digits in length. No, I've never seen a 13-digit one myself, I have to say. Like why would I see them anyway? American Express cards, I believe, start with 34 or 37, and they're 15 digits long. MasterCards, 51, 52, 53, 54, 55, 16 digit. Discover, which is a little used American card. I don't think you'd see any of them here. 16 digits. And then Diners Club can be that range of numbers there as well. And they're all 14. So actually, from even looking at the start of the number, you could even tell what kind of a card it is. I saw a website once which was very clever because it asked you for your number, and once the number looked correct, it put up the logo of the card you were using, and you're like, how do you know? Do you know? But looking at the number, you can tell what kind of card it is. So I thought that was very, very clever.
So they typed in 6011 and then the Discovery logo would appear.
No, they typed in 60011, the other 12 digits, and when all the ducks were in a row, then it displayed the Discovery logo. But I thought that was very, very clever. And it's interesting because a lot of time when they ask you for the number of the card and the kind of card, there's no need to ask them for the kind.
Why?
But if they ask you, that's an extra piece of information. If they don't match up, then obviously something's wrong.
They should know that.
But they should know just from looking at it. No, they should know. That's just the client. That's just the browser. So if the number then doesn't look right, the browser won't bother sending it off. Just saying, look there, there's something wrong with that. You know? So it's quite clever. So it has a very good chance of catching. The most common mistake is where you swap two digits around. So instead of saying 4599, you might say 495. Well, you wouldn't ever do that, but anyway. If you swap digits around, it catches that.
If it was like 62 and a 67, you might do 6762.
You might mix them up. You know? So it's very good for catching digits that have been interchanged. Generally, if you were to do the maths, if the one number at the end can be anything, then you're talking about, I guess, a random number would be caught 90% of the time. You know, if you randomly make up a number, you've only 1 in 10 chances of it being actually right. No. ISBN numbers in books, although there's actually a newer ISBN now. There's ISBN 13, it's called. But if you get an oldish book, this was the part of the class where I used to say to people, right, take a book out of your bag. Who carries books around in their bags? Not computing students, anyway. So every book has a unique number on it. So you go to Amazon or whatever, you can put in the number and order the book. So it helps you, it's like it's a unique number for every book. The way that works is, now this is a very common kind of check digit setup, okay? This is very typical of how they work. So the first digit is multiplied by 10, the next digit is multiplied by 9, the next digit is multiplied by 8, the next digit is multiplied by 7, and by 6 and 5 and 4 and 3 and 2 and 1. Again, if you're confused about which way it would work, it would never make sense to multiply the check digit, the one at the end, by anything. So that's always just left by 1. No. You add them all up, and you do a mod 11. Now, when it comes to checksums, we see mods a lot. Okay? So if the number mod 11 is 0, then it's valid. So in this case, a randomly generated number would have a 1 in 11 chance of being correct. Can anybody see anything wrong with this super brilliant plan? What possible values can mod 11 give you? What's the lowest value it could give you? 0. What's the highest value it could give you? 10. Do we have a digit for 10?
No, whatever.
There's no digit. There's no, like, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then what?
8.
So, well, no. Actually, it was X. So they went for X. So sometimes on an old ISBN number, you'll see an X at the end. And that X stands for 10, which it has done for about 2,000 years now. The Romans. So, in Roman numbers, X was 10. So, if it's X, then that's 10. So you multiply X by 1 equals 10. Then it all adds up. Okay? Now this is actually the old format for ISBN numbers. So newer books don't have the old one. Okay. Any questions on that? So that's a beauty for programming lecturers, because of course you have to handle the exception with the X. Now, generally, you see mods a lot when you're talking about checksums. Okay? Now, you could probably have a whole couple of lectures on the maths of all this, if I could understand it all. But there are some general rules if you're designing a scheme like this. Okay? Generally, the mod that you choose needs to be greater than the number of digits for it to work well. And it needs to be greater than any than the range of any single digit. So if the digits can go from 0 to 9 or 0 to 10, then for it to work well, you want a mod 11. And also, prime numbers work better. So in modulus algorithms, you see things like mod 11, mod 23. I haven't seen a mod 17 actually, but that would be a good one. And not to be outdone, French ID numbers use 97.
97.
Yeah, which is a prime number as well. Okay. So everybody get the idea? So the last digit is based on the rest of the data. You do some calculation which gives you what the digit should be, and if it doesn't match, then you know something's wrong. So either someone has made a mistake, or someone is having you on. No. PPS numbers in Ireland, the letter at the end. All familiar with that? You should all be, because without a PPS number you can't be here actually. So everybody in the class has got one. Even the people who are only here temporarily, you've all got one. So every working person in the Republic of Ireland has a PPS number. It turns out now that you're assigned them now at birth. You used to only be assigned them when you started work, but now you're assigned them at birth. And there's actually very strict regulations about who can ask you for your PPS number, for example. Like, the guards can't ask you for your PPS number unless you're like applying for a job in the guards. Do you know what I mean? Like, if they want to pay your tax, if they need to give you money, they need your PPS number. But they can't ask you for that. So there are very strict rules about who can even ask you for your PPS number. But it varies from country to country. I was ordering a magazine yesterday in Spain, and they wanted my ID number. I was like, why? And they just weren't having it. There was no way around. Now, thankfully, I actually knew how to make up one. Because I knew the algorithm for the checksum. So I was able to make one up. But you would think buying a magazine, you wouldn't need your ID number. So it varies very much from country to country. In the US, they're notorious for looking for your social security number for anything. Okay? So in Ireland anyway, looking for your PPS number, there are very strict rules about who can even look for that. And very good reasons for that. Okay? So it's 7 digits followed by a letter. Now, so again, if you're trying to remember how this works, you're never going to multiply the check digit part by anything. You're never going to multiply the last digit by anything. So we have 2, 3, 4, 5, 6, 7, 8 there. Okay, so you multiply the first digit by 8, the next digit by 7, the next digit by 6, the next one by 5, and by 4, and by 3, and by 2. Okay? And it gives you a number. Right? So you do a mod 23 of that number, and that gives you a smaller number between 0 and 22. Okay? And then you figure out what letter that should be. So if it's 1, it's A. If it's 2, it's B. If it's 3, it's C. If it's 4, it's D, and so on. If it's 0, well, this is the thing. I wasn't sure how this worked, but it turned out I was in the pub one night, and a buddy of mine actually had a W in his PPS number. So it's if it's a 0, it gives you W. Okay. So this scheme makes sense, but you could see it wasn't designed by a programmer. Okay. A programmer would have gone A 0 is A, B is 1, and like that. Okay. Because that W is 0 is just troublesome. Okay. But it works quite well. Now that W is not to be confused with the wife W, right? Until quite recently, like my mother, for example, would have had my dad's PPS number, but with a W at the end of it, for wife. Okay? Whereas nowadays, women are considered people in their own right. And so women have their own PPS numbers. But that's why a lot of times when you're filling out a form and you're putting in your PPS number, you're like, oh, I'm missing a digit. That's for the wife. So someone might be 6059922HW. This could be Mr. Smith, and Mrs. Smith would be that number with a W at the end. Now that's being phased out. But actually, even what I found interesting was on the form for my children's allowance, when I was filling that out, there was slots for both parents' numbers, and there was space for W's in each case. Which, if you think about it, was an interesting administrative choice on behalf of the state, because it was accepting the possibility that both parents could be women. Or else they were just so used to copying and pasting in the piece in the form. But anyway, I digress. Okay? Now, so that's kind of discontinued now at this stage, really. But you could see how it would make an assignment in this even more complicated, because you'd have to, it could be 1, 2, 3, it could be 8 characters long or 9 characters long, provided that the one at the end was a W. Okay? So if you don't have a credit card, well, at least you know you have a PPS number, so you can try that one at home. And maybe you'll find a book somewhere, and you can try the ISBN one. But it has to be the short ISBN number for the one I showed you so far. Hopefully you've all got some actual cash in your pockets. Okay? So for Euro banknotes, there's a letter at the beginning. Right? And the letter tells you the country where the note was printed. Who knows how things might pan out, but if I had ones that were printed in Greek, I might spend them if I had them. But so it tells you the country where the note comes from. Interestingly, there are slots for countries that aren't in the euro yet. Well, they might never be allowed to print their own money. We'll see. But now that's going to change, I think. I think it's going to change so that they'll use the 2-letter code for the country soon. Because, of course, remember, if you only got 26, you're going to kind of run out sooner or later anyway. They were in order. If you can Google this or Wikipedia this. The letters were actually in order of the name of the country in the language where the country is spoken. So, like Austria would kind of been up there towards the top. Although they did have to do a swap, because when they did it that way, they discovered that the letter for Greece was one of the letters that doesn't occur in Greek, which was a bit of a problem. So there's a bit of a swap there, but again, I digress. So the letter gives you a number: A equals 1, B equals 2, C equals 3, and so on. Now, if you were writing a program to check these, you might actually be very pedantic and check if it's a country that actually prints euro. Do you know what I mean? So if you have a note that's allegedly a 10 euro note from the UK, well, even if the check digit is correct, that's probably a bit fishy. If you edit the code, then yeah.
Too specific in a way.
It could be too specific, yeah. But at the same time, I mean, if you're accepting, you know, UK €10 notes, I mean, that's probably going to be bad for your business, like, do you know? So, I mean, no. So that gives you a letter, sorry, that gives you a number, and then you add up all the digits, and that gives you a number. Then you add those digits again, as often as is required, and that eventually gives you a number that should be 8. Now, that again is a pain to program, and it turns out that the following also works, but I couldn't actually tell you why. I asked a math person, because it seemed to be always true, so I asked a math person, is it actually the case that it's always true? And they said, blah, 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 blah. And I said, great, thanks. So if you treat the number part as an integer, as a big integer, okay, and you add the number that you got from the country to it, right, and you do a mod 9, you should get 8. Okay, so it's the equivalent, this adding digits together is the equivalent of doing a mod 9, which we were kind of claiming for the credit cards, but we saw that it didn't hold up exactly.
Yeah.
But that's the same claim we were making for adding the 2 digits together. So if you treat the number part, so here if you take this, you know, 4, 1, 3, 5, 9, 8, 1, if you treat that as a big integer, now your types will be important in your code here. I mean, if you start doing this in floating point, like, all bets are off. You treat that as a big integer, get the x, which would be 24, add that to the big integer, do a mod 9 of that, you should get 8. Okay? So that's something for you to try as well. With your money at home, you'll be up all night with the calculator. There's a Finnish guy, he's not in this class, is he? No, no. This is the Finnish SOTU, S-O-T-U. As far as I know, they've actually changed the name of this since, but this is basically Finnish PPS number. I was just looking for other examples. And again, this is quite typical of what you might get, okay? Although I think the Finnish one was designed by a programmer rather than an Irish civil servant. So the first 6 digits of the Finnish number are the day you were born. Okay? So that's embedding some information there now. So, like, I bet on a form, you know, to do with things with the Finnish government, they ask you for your ID number. There isn't a separate section where you ask your date of birth, because that wouldn't make sense, you know. So you have like day, month, year. Now, as we saw with the Y2K bug, you know, you can actually, if you're using just 2 digits for the year, you can actually get into trouble. So the next character is a separator. So it's a plus for people born in the 1800s, a minus for people born in the 1900s, and an A for people, born in this century. So I guess this system goes back a while, if they had to worry about people born in the 1800s, or else Finnish people live long, healthy lives, do you know? But I guess, I mean, I finally got onto the, okay, no. So if, I guess, I mean, if you were devising this, if this system was around in the 1960s, of course, then someone who was 70 would have been born in the 1800s, you know, so that's not, no. The next 3 digits then are assigned kind of on the day, right? And what they do is they give you an even number if you're female and an odd number if you're male. So again, that's some very clever embedding extra information in there. So from the number, you know the date someone was born, and you know whether they're male or female. So those are 2 things you don't have to ask. Okay? It does mean, though, that only 500 men can be born in Finland in any one day, but Finns aren't reproducing at a sufficiently alarming rate for that to be a problem in the short term. Okay? Currently, there's only about, you know, less than 100 babies born a day in Finland, which isn't that many. Oh yeah, yeah. Maybe there's less than 100 men. Even so, even if there was 200 people born in Finland a day, that doesn't seem like a lot.
Well, there are 4 million altogether.
Is that all?
Yeah.
All right, because you easily have 200 babies born in Ireland in a day, I'd say.
Same population.
Do you know? The last digit then is, surprise, surprise, the Czech digit. Okay? And what you do is you ignore the separator that gives you the century, and you treat the day, day, month, month, year, year, 052 if you're the 52nd female born in Finland on that day. You just treat that as a large integer, and then you do mod 31. Okay? Now, this is where it gets interesting, right? So then, if you get 0, you get 0. If you get 1, you get 1. If you get 2, you get 2. If you get 3, you get 3. If you get 10, you get A. 11 is B. So far, so good. But look at the string. There are 31 possibilities, aren't there?
Yeah.
There's no O.
There's no O. What else is missing? I. Q also. G as well. Okay. What do we know about Z? What do we know about O, I, G, and Q? Well, actually, they don't use them in Finnish. Would be a good answer. I don't think it's the answer though.
They're easily confused with digits.
They're easily confused with other characters. So, like, if the Czech letter was O, right? If you're supposed to put O at the end of your number, and someone wrote down O, do you know, is it 0 or is it O? You know, what? Really? You're joking. Okay. So, well, there's a good example of why you wouldn't use O as the Czech letter. I can be confused with 1. G could look like a C. Q could look like an O, I guess, on a bad day. You know? Yes, sir.
When you get our student number, or 000, blah, is there actually the same, some kind of method like those?
The question is there a Czech digit at the end of CIT student number? I don't know.
But like, why is it 3 zeros?
I guess there just aren't as many. I guess we're just accounting for the possibility that, like, if you only had 5 digits, you would have to start reusing numbers eventually. I know there's a Czech digit at the end of the CAO number, but it's like a secret how it's calculated. I tried to find out and I couldn't.
It's a secret.
It's a secret. I thought it'd be a very good example, but it's a secret how it's done. So that's quite clever, I think, because of course it's the whole purpose of the Czech digit is to catch mistakes. You don't want to then have a system where, mistakes are common. I mean, 0 I know is a very common mistake to make. Okay, now let's look at some more. Okay, the People's Republic of China, there's a mod 11. The UK uses Czech digits. In Italy, you could tell what your mother had for breakfast on the day you were born, pretty much, from someone's ID number. It's very, very detailed. Okay, and the US and Canada share a numbering system. So if you're Canadian and you go to the US, you can use your number, but only the Canadians use a checksum.
What if they didn't have breakfast on the day you were born?
Well, I was exaggerating.
Oh, okay.
Sorry.
Don't worry.
Sorry. No.
I'm curious.
Okay, just when you said that late. No. So like I said, your CEO number is a secret. I have here, if I can find it quickly, Spanish. Well, I have it on a handout. I can give you the handout, okay? So Spanish numbers also use a letter at the end. So that's another one to look at. And what I will do is, I was going to show you the code as well then, how you might actually, so this code here, which this is on the blog, so you can just follow the link. This is using the sort of beautiful people phone number algorithm, just to check that the last digit is the number of even digits in the rest of the number. And what we'll do in the next class is we'll look at how this form, this, so the idea is basically you put in the number 087, 1, 2, 3, 4, 5, 6, 7, and then you check it, and that didn't work there. No, there must be an image missing. Oh, it's because I'm disconnected from the web. Okay. Actually, that's a very good example there. Look, the way that code was written. Remember I was saying the last day, you can preload the image when the page loads, or you can, when the person clicks, go get it then. Well, of course, I couldn't go get it because I was booted off the network. So that's another good reason, that's why that didn't work there. So you can look at that on the blog and the slides and examples thing, and see if see how that works. So that's going to deal with sort of the interaction between the code and the DOM and the checksum. So it'll all be in there. Okay, so we'll look at that in the next class. Any other questions or anything?